There is one subtle piece of wording that we need to talk about now that we're in possession of Euler's number that is unnecessarily confusing. We said a value decreases by 4% each year to mean that each year the value is multiplied by, well, 100% minus 4%, or 1 minus 0.04, is 0.96. So the value decreases by 4% each year means the value is multiplied by 0.96 every year. If we say a value decreases at a rate of 4% per year, this should mean the same thing. Unfortunately, it doesn't. Hidden in this statement is a 4% of its current value. And what this phrasing says is that at any given moment, the rate at which it's decreasing is 4% of its current value per year. If its current value is 100, at that instant it's decreasing at a rate of 4 per year. So, we need calculus to deal with that notion, but I can tell you now what the result is. We use this phrasing to describe what we call continuous change, which is a concept analogous to continuous interest compounding. So, when we have continuous exponential growth or decay, also a misnomer because it's always continuous. But this is the terminology we use. This can be modeled by a function of the form f of t is some starting value times e to the power of something times t. And we call r the rate of growth or the rate of decay, and often express it as a percent, by analogy to what we did with interest. This is weird language, but we get used to it. Here's an example. Suppose the cost of goods increases at a rate of 3% per year due to inflation. So that means that the rate, at a rate of 3% per year, that's the key phrasing that tells us we want to play this continuous game. The rate is 3% or 0.03. This is increasing, so we have a positive rate. Our starting amount, well, we have an item that costs $800 today. So its cost after t years is given by 800 times e to the 0.03 t, which is a very easy function to write down, so at least that's nice. Now let's see an example where the amount of something is decreasing. In this example, the amount of a drug in a patient's system decreases at a rate of 12% per hour. So, at a rate of per hour, we have that very specific phrasing here. Our rate is negative 12%, which is negative 0.12. And this is negative because the amount of the drug is decreasing. When something is increasing, our R is positive. When it's decreasing, our R is negative. And then we had an initial dose of 50 milligrams. So the amount of the drug in the patient's system after t hours is 50 times e to the negative 0.12 t. So that's all there is to this. We just have to be alert for when this is happening. In real life, it's always clear which one of these we actually mean. But because the phrasing that we use differently is so subtle, in math class, it's sometimes hard to be sure.